Hi everyone, welcome to another lecture on neural networks. So today I want to talk about the approximation properties of neural networks, about backpropagation, about training in batches or mini batches. Then we want to talk about regularizations in neural network and finally about training neural networks. So neural network can approximate any function, well, any continuous function with some other small details. They just, in order to do that, they just need a single hidden layer, and you can approximate to any degree of accuracy. So that doesn't mean that you may be able to learn this efficiently, or they may be able to generalize it correctly. It just means that given a function, not a training data, but a function, you can approximate to a neural network to any degree of accuracy to that function. It may take, for example, an exponential number of hidden neurons to do that. Kind of the positive thing about this is that really neural networks can learn very complicated nonlinear decision boundaries, like in these examples here. So they are more flexible than, say, a linear model, right? A logistic regression model that just learns linear boundaries. So, and this is, one of the powerful properties of neural networks. So I just wanted to mention, because people talk a lot about what is backpropagation. Backpropagation is kind of a very kind of word people talk about out there, right? And so backpropagation is just an efficient algorithm that computes the gradients of the parameters of the network. So it's nothing very fancy, but it's important to know what it is because you're gonna be asked about it. So I want to talk about regularization in neural networks. First, let's start by talking about what is regularization. So regularization is any technique that prevents overfitting. So we have several methods to avoid overfitting in neural networks, and that's basically what I'm going to talk about. So the first one is called dropout. So how dropout works. So you have a network. Think about this like network that I'm picturing here. A is called standard neural network. And what you do is that you take a layer, and with probability P, you drop some of the neurons on that layer, some of the nodes on this network. Okay? And with probability 1 minus P, you keep the node. So for example, we take the first neural network that you see here, and randomly we drop some of the nodes of the network, and then we keep what we see on the right. So what's going to happen is that we're going to train with this second network. Now we're going to do this on one batch of data. On the next batch of data, we're going to randomize again and pick some other values. I want to keep doing that, basically. So at every batch, we're going to pick the nodes that we're going to drop, and we're going to train with the rest of the nodes. So this process works a bit different in training and in testing. So in the training phase is basically what I just told you. So you are going to train at every iteration with a slightly simpler network, okay? Now at the testing phase, what you do is that you are using the whole network. Now, to account for the fact that you drop in the training process, you drop nodes, you have to multiply the activation by 1 minus P. And that accounts for this missing of the nodes at training time. So why is this any useful? Well, the first thing is that it's been shown that when you use dropout, you can reduce the test error. on many architectures. So this is this plots I have here is from a paper, a Dropout paper, that they show how they can get better classification error by using Dropout in multiple networks. So why is Dropout really, what is it doing? Why is actually working better than a regular network? So it turns out that neural networks learn co-adaptation of some of these hidden units that can work on training data, but don't generalize well to data that is not being seen by the model. So what these dropouts do is that they break up these adaptations, making the presence of a particular node or a particular neuron unreliable. So now the network has to learn in a way the same model in kind of in different ways, basically, without relying on a particular node, because a particular node may not be present there. And that's basically, in that way, regularizing the network. So Dropout is kind of one technique that we have. The second technique that we have, we already have talked about it, is for example, L2 regularization or L1 regularization as well. So L2 regularization is called weight decay in neural networks. So it's the same thing. So what we do is that we add a penalty to the loss function. So we add the norm of the L2 norm of the parameters. So what happens is that we have a parameter lambda that is gonna decide the trade-off between how much we try to optimize the error function and how much we try to shrink the values of these parameters. So larger values of this lambda will tend to shrink the weight towards 0. And as we know, we use cross-validation or validation to estimate the values of lambda. So there is another technique that is particularly useful when you have images that is called data augmentation. So and the idea is that, so you have a little kind of cute picture of this cat, but if you rotate the picture, or maybe you zoom into the picture, or you change a little bit the color of the picture, it's still a cat. So then what you can do is that instead of just using one picture, you can do all of these things to at every iteration give the network a slightly different picture of the cat. So it's the same picture, but it's been rotated, translated, maybe deformed in small ways, but in a way that we still see a cat, right? So the label is not changed. So that's very important. You cannot, the whole point is that we change the image but keeping the label, otherwise it's not very useful. So we are creating fake data in that way that has the same label, and in that way we're going to have more data. Here are some of the augmentations that you can use. So we can use rotation, crops, flips. We can add noise. We can do scaling of different ways. So people have also thought about how to do the augmentation for text. It's a little bit more difficult, but you can think about a synonym replacement, random insertion, random swaps, random deletions, and things like that. So this is kind of one way to do it. There is a smarter way in which people have thought about doing that augmentation for text, and think about it's called back translation. So, and the way you do it is that you have a sentence, you take that sentence and translate it to a different language, say French. So you take your sentence, take it back to, translate it to French, and maybe to German, and maybe to Spanish, okay? And then you take that and translate it back to English. So when you translate it back to English, you're gonna have a slightly different sentence, okay? So, and in that way, you do the augmentation for text. Another technique that we have for avoiding overfitting is early stopping. So, and probably you guys have seen this before and you even have done it. So when you start training your model, you have to decide, how many epochs I'm going to train this model for. And you may have seen that as you train your model, the validation error is going down, 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 but at some point the validation error starts going up, right? So what early stopping means is just that you keep the best model you have seen on your validation data. Either you stop the process, or more often you just let it run, but you just keep the best validation you have ever seen. So these are some of the tricks you can play to improve your performance. So now I want to talk a little bit about mini batch stochastic gradient descent. So I had a few conversations and questions yesterday in office hours about this. So I wanted to kind of make sure that we talk about it. So the batch size, just to get some definitions out, the batch size, the number of samples that you use per iteration. So we are doing gradient descent or stochastic gradient descent. It's called also mini batch stochastic gradient descent, and we're using a batch size. So we are at every iteration just using a number of observations. Now the number of epochs is the number of times you see the whole training data. Okay. So mini batch stochastic gradient descent is a variation of gradient descent in which you split the data in smaller pieces, and then you update the coefficients after seeing each of these pieces. Again, maybe you have 1,000 points observations and your batch size is 100. So in one epoch, you are going to update your coefficients after you see 100 observation, and then you're gonna do it again, and then you're gonna do it again. Okay, so you're gonna do it multiple times after you have seen 100 observations. So why do we use mini batch? Well, it could be as simple as you have a problem with images and your images don't fit on the GPU. So all your images don't fit on the GPU, so maybe you can fit like 32 images or 64 images, or these days you can play a couple of tricks and maybe fit even 700 images, but that may not even be your whole data set. So you have to do many batches. So there are a few papers talking about the fact that small batches can offer some regularizing effect to the models, that actually just making smaller batches gets you to better optimization, better minimas, better models, more regularized models basically. And possibly this is due to the fact that by doing that you are adding some noise to the learning process. But we don't understand very well this, but it's written in many papers. So another thing that we want to think about is that when you are using mini batches, like the example I gave you before, you have 1,000 observation, but you're updating every 100 observations. So you are updating your model many more times than when you update just one time with 1,000 observation. It is true that the gradient that you compute with 1,000 observation is more accurate than the gradient that you compute with 100 observations. But the fact that you update 10 times may be more important than the fact that the gradient is more accurate. And actually, as I said before, it may be even better that there is some noise in the process. So this is still something that people are trying to figure out, but I just wanted to give you an idea of why we may try to decide what's the best mini batch size for our problem. What are the limitations or the trade-off that people think about? So now let's talk for a little bit about learning rates. So learning rates is the most important hyperparameter to tune your neural network. As we know, if learning rates are too small, your training is very, very slow, okay? And if learning rates are too large, your training diverges. So in the conventional wisdom, what people do is that you fix learning rates and you train for a while on the same learning rate. And then once your validation stops improving, you lower your learning rate by 5, by 10. You divide your learning rate by 5 or by 10, and then you keep that new fixed learning rate for a while, and you keep doing that. So people are doing many different other ways of changing learning rates, and I am going to talk today about one of them. So there are different theories of what works, but this is kind of one of them. So there is something called cyclical learning rates, and the idea about cyclical learning rates is that you go up on learning rates and then down, and sometimes you will do multiple times up and down on learning rates. And here is some experiments, some results of some experiments. So the red line that you see there are the experiments with cyclical learning rates, and as you can see, they get to a very good result, even better than the other one, with just 3,000 iterations instead of with 7,000 iterations. So it cuts the amount of time by a lot. So let's talk about how we do this. So first of all, there is something called the learning rate range test. Okay, so how you do that? So the idea is to try to find reasonable learning rates for your problem. So what you do is you start with very low learning rates, say 10 to the minus 5, and you increase linearly your learning rates until a maximum, for example, of 1. Okay, and then you plot your learning rate versus your loss, and you get a plot like the one I'm showing you here. Okay, so note the value when the loss starts to decrease and when the loss becomes kind of increase or becomes kind of random. So we basically would like to concentrate on this range of learning rates. So the beginning, when the baseline rate is the learning rate when the loss starts to decrease, and the max learning rate is the loss when the when the loss starts kind of increasing or becoming kind of random in a way, like the way you see it here. At some point also the loss is going to go up very high as well, but I am not showing it you in the picture here. So when you see the noise, then you that's what your maximum learning rate is. Not all that range test looks like this, unfortunately. Some of them are not as easy to interpret. So this is something that you can do and see if it works for you. Otherwise, you're going to have to experiment with different learning rates. So then, now that you have your base learning rate and your maximum learning rate, there are different things you can do with it. So one of them is called triangular learning rates. Is that you go up and down in between your base learning rate and your maximum learning rate. And you do that several times. So that's kind of a simple strategy. So, yeah. So one question that you may ask is, why is these cyclical learning rates why are they working? So it turns out that, and you may have seen this maybe in some of your experience, that when you're training, at some point your loss stays for a very long time in a plateau. It just basically stays there. Just your training loss just doesn't go anywhere. It just stays there for a while, and basically what happens is that you are in something called kind of a saddle point. So it's basically we have this like huge space of weights, right? So it's a huge multi-dimensional space, and you got to a point that it's not a minimum, but it looks like very flat for a very long time. So you should be able to escape it, but you are basically there for a while. So the idea is that changing learning rates may help you escape those places, these saddle points, more rapidly. So there is this another strategy, which is the one I use right now more often, that is called one cycle learning. And the idea of a one cycle, or one cycle triangular learning rate policy, or is basically to go first to go up and then to go down. It's just one cycle. So suppose that you decided to use 10 epochs for your cycles. So you multiply the epochs by the number of batches you have, and this is the amount of iterations you're going to have, and you're going to use one cycle over all of those iterations. Okay, so your model, your learning rates are going to go up one time and then down. Okay, if you want to try to change this, you start from scratch again, so from a random model again. Okay. Yeah, so this is, I use this a lot. It works in many cases better than just using fixed learning rates. And basically the code right now, PyTorch also has this code already in PyTorch, and I forgot exactly how it's called. One cycle something is called. But also it's kind of very simple to write this code to make this a cosine triangular learning rate, how it's called. So it's very simple, and then you can see what are the parameters you can change here, right? So the main parameters are the maximum learning rate you're going to, and then how low you want to start, and then once you go up, how low you want to go on the other side. So those are the things that you have to decide. And they may be different for different applications, right? So now I want to talk about batch norms, which is something that you have seen that I use in some of the neural network examples that in particular one for the homework. So and basically batch norm is normalizing the inputs to every hidden layer. So we know that before we pass our data into our model, we should normalize, because basically it helps the model trains faster, and it helps with training instabilities. So you always have to normalize before you use linear models or neural networks. Okay, so that's the input, right? So the issue is that people realize that normalizing the input is just not really enough. So that basically the layers themselves sometimes have very different scales, right? So what this idea was that why don't we normalize the layers as well? So what batch norm is doing is basically first normalizing the layers, and then learning new parameters for the shift and the scale. Okay, so the equations are not very difficult. You use the mini batch mean and mini batch variance to normalize, and then you learn, maybe your network actually wants to have a different mean and different variance, so you add these two parameters so the network can learn if it wants to add a little bit of a mean or variance to a shift and a scale to the network. So batch normalization has parameters, right? So because again you first normalize with the mini batch mean and mini batch variance, but then you let the network learn its own mean and variance, basically, again, in case it wants to correct for what it just did. So batch normalization is basically, again, similar to the way we normalize our inputs. We are trying to normalize the hidden layers. It acts as a form of regularization to the network as well. This has been shown. It also allows to use of higher learning rates. It improved the gradient flow through the network. So it's the same idea that so basically the normalized hidden layers improve how the flow goes through the network. It can be interpreted as doing pre-processing on every layer of the network. Has some learnable parameters, so you have this shift and scale that you're learning. And it also reduces the strong dependencies on initialization. I'm about to talk about initialization as well. So basically, neural networks are difficult to train, and batch normalization is another one of these tricks that is used to make neural networks train better, basically. So by normalizing the internal layers of the network, we are able to train better this neural network. So that's kind of the main point. So another one of those tricks is weight initialization. So basically, if we just initialize the weight with any random number, it doesn't really work very well. So there are different, this is an area of research, people have papers about this, but basically for example, one of the heuristics that people use, and probably the one that PyTorch is using right now, is basically say, well, if I have a linear layer, okay, if I have a linear layer, what I want to do is to initialize all of the, so if k is 1 divided by the number of input features, I am going to initialize the weights with numbers that are uniform between square root of k and minus square root of k and square root of k. And these and many other initialization technique improve the rate of convergence of the network. So basically, just any uniform or any random number is just kind of not going to work. So we want to be careful on how we initialize. Okay, and this is the end of this lecture. Here are some references. Thank you, and see you in the next video.